All right, let's talk about the mean value theorem and L'Hopital's rule. This chapter is more theoretical and deals very much with concepts, very critical concepts in calculus. So we'll be talking a lot about pictures. Let's look at this picture here. Now, we often think of graphs as showing distance versus time. So think of the x-axis as time and the y-axis as distance. So these could be meters or miles or something like that. So here, according to this solid line, we start at 0 and we end up after 2, which could be 2 hours, I suppose, at 150. All right. From that, we get an average speed. Average speed is 75, 150 over 2. Now, according to this graph, there are two legs of the journey. First leg, 100 velocity. Second leg, 50 velocity. What's happened here? Constant velocity and then a sudden change in velocity. Now, he started out going faster than the average velocity. In order to end up with an average velocity of 75, it stands to reason that he's going to have to slow down at some point. He can't just keep going at faster than 75 and end up going an average velocity of 75. So the velocity must have decreased. All right. But in this case, there's a sudden change in velocity. The velocity is discontinuous. Now, distinguish here between the continuity of the function and the continuity of the velocity. The function is continuous. Remember, continuous means the function doesn't jump. Here, the traveler is traveling continuously. The traveler doesn't jump. The car or whatever it is, always, if there's a small change in time, there's a small change in distance. Of course, the other way of thinking about continuous function is you can draw it with your pencil without your pencil leaving the page. All right, the function is continuous, but the velocity is not continuous. It's 100 here, it jumps to 50 here. All right, and there's no point at which the velocity is equal to 75. Now, suppose the function is continuous and the velocity is also continuous. All right. If the velocity is continuous, it starts out more than 100. At some point, it's going to have to dip below 75 in order to get an average velocity of 75. If the velocity stays above 100, there's no way to have an average velocity that's less than 100. Okay, so the velocity has to dip below. Now, if it dips below and the velocity is changing continuously, at some point it must be 75. All right. We can draw a picture here to show this. Okay. We started out, well, the function starts out, as we see this picture, the function starts out at 0 and ends at 75. But if I draw the velocity as a function of time, time t equals 2. Okay. The velocity starts out at 100. Okay. And the average velocity is here. And at some point in this interval, it has to dip below 2. Now, it could end up above 75. Sorry, it's not dip below 2, dip below 75. At some point, it has to dip below 75. So let's say it dips below 75 here. So I don't know what time this is. I'll call it t equals c. So if the velocity is continuous and it goes from this point to this point, at some point, it must cross the line here. So that's the intermediate value theorem. Okay, so the mean value theorem and intermediate value theorem are very closely related. But that's what's going on here. As I said, it's not necessarily true that the velocity ends below 100, but if I'm going to take the average, it has to go down. Now, if you remember that average is something like integral, if I continued this function like this, say, and the area, well, that's not a very good continuation. If I do something like, whoops, if I do something like this, Okay. If you think the total area under this curve here is the same as the area on this, under this rectangle, then that's the same thing as saying that the average value of this function is 75. All right. But it's got to cross at some point. Right. So that's your mean value theorem. Mean value theorem. The mean value of the velocity must be equal to the velocity at some point in between. All right. So here's the formal statement. Suppose f is continuous in the closed interval and has a derivative everywhere in the open interval. Then the derivative is equal to f prime at some point. Now, notice here that he's not talking about the continuity of f prime. But it turns out that if f prime exists everywhere, it must be continuous. We can see that up here. Here, there's no derivative at this point. But what's happened here, if there's no derivative at this point, it's because the limit of the derivative on this side is different from the limit of the derivative on this side. Since the derivative itself is a limit, then in order for the derivative to exist, these limits must agree and the derivative must be continuous. All right, so that's kind of a key point here, that if the derivative exists everywhere, it must be continuous. So how do we prove this? Well, what we do is we transform this problem to a special case, which is easier to consider. This is the special case when the function is 0 at both endpoints. Okay, we can draw that picture here. It's an easier thing to consider. Now, you would think that this is not going to cover all cases, but in fact it does. All right. So in this case, the function is not equal at both sides. Well, all right, so this is the derivative. Suppose I have a function that looks like, as he showed, my original function may look like this. Something like that. And I want to transform to the case where the function begins and ends at 0. All right. And the way I can do that is I simply take my original function and I subtract the line that goes from here. So if the green is my f of t, and I can call this one, let's just call it a of t, or let me call L of t, which is a line, then f of t minus L of t is going to be a function that starts and begins and ends at 0. It looks something like f of t, but it's kind of rotated down. Okay. So you can see, so I'll call this g of t. Okay. So you can see g of t is closely related to f of t. And we're going to transform the mean value theorem statement about f of t to a statement about g of t. Now let's see how that works. Okay. All right. He's got the same picture here. All right. Except he calls this new function, f of t. So here was the original function, and here is the transformed function. So you can see that if the slope of this transformed function is equal to the average slope, that's the same thing, if the slope of my original function is equal to the average slope, that's the same thing as saying the slope of the transformed function is 0. Let me show it on my case also. Here you can see this green one here, this green function here. This slope is parallel to blue, something like that. Okay. And at this point here, where they're parallel, if once I transform it down, that's exactly a point where the slope is 0. Right? Because what I've done is I've subtracted a function whose derivative is equal to the average slope. So at this point here, average slope is equal to, so here this is, I can say f prime of, let's call this, I'll call it t0. is equal to f prime average. And then at this point, I have g prime of t0 is equal to 0. Okay? Because L of t has slope equal to f prime average, when I subtract, I'm going to get 0. Okay? All right. So that's the way you can actually prove it. If I can prove this Raleigh's theorem now, which is the case when f of a equals f of b, then all I have to do is add back the linear function, and I get my general case. Right? Okay. Well, we don't actually have the proof of Raleigh's theorem, but you can see that if I did have the proof of Raleigh's theorem, that would give me the proof of the general theorem. All right. Now here's another way of phrasing the implications of this theorem. Here it says, so let me copy this and we'll talk about it. Or here he says the derivative at c gives an exact prediction of f of x. All right, so let's draw a picture for what's actually going on here. Here I have my a and my x. Okay, so let's say a is here and x is here. Actually, x could be on the other, x could be below or above. We typically draw it above, but it could be below if I wanted to. So here I have f of a and f of x. Okay. And just to make things different, I'll put f of x down here. All right. Now what he's saying is that, well, here, let's draw the function here. The function starts here and it goes there. So it starts out like this. Okay. It ends up going down here. Okay. Now, it's obvious that if I take the derivative at a, this linear approximation here, y equals f of a plus f prime of a times x minus a. It's obvious that this point down here, this f of x, is not on this line. But what the mean value theorem says is there is some point c. Well, here, let me draw the average line so that we get this correctly. Here's my average line here. All right, this point down here is on this line. You're saying there's some point c where I can find the derivative f prime of c. Sorry, that's not very good. It should be parallel to the other one. All right. So this is the derivative. Slope is f prime of c. There's some point c in between where I can take the derivative from c and the value from a and put those together and get a straight line that passes through f of x. So this is the point x f of x. Okay. So notice that this is not the tangent line at c or the tangent line at a. It takes the value at a and the derivative at c and puts those together and gets a linear approximation that passes through x. And the important thing is that c is between a and x. I can find some c between a and x. That makes this happen. So again, I have my function at a, my derivative at c. I put those together and I get the value of the function at x. So I'm going to stop here, and in the next video I'll show how this fact leads into L'Hopital's theorem.